All right, let's get started. Does anyone in the audience have any announcements for the group, like you're looking for a job or your company is hiring, or even something like you want to talk to someone in the audience about some API, anything like that? Okay, I got an email from a company that's looking for Python developers, and the company is Tachius. They're an oil and gas company, and I left some descriptions of the job on the table in the back, and I also have some here. So if anyone's looking for a job, you can see me at the end. And also, we need more speakers and volunteers to help us find speakers. So if anyone in the audience would like to do that, please see me or Peggy at the end of the talk. Tonight, we're very fortunate to have an expert in machine learning and artificial intelligence. Our speaker is the founder of Vitruvian Science. Please welcome Marcus Beisinger.
Hello. Okay. Hi, everyone. My name is Marcus. Let me go to the slides here. My name is Marcus. I'm the founder of Vitruvian Science. My co-founder, Sherjil, is actually in the audience today. And I'm going to do a little bit of a hands-on with you guys today on demystifying deep learning, coding it up. We're going to have examples. We're going to get and do some math, and it'll be great. The slides I can send out as a link in the Meetup group email or later, and you can see the code on my GitHub page here that's going to be used in the examples. Cool, so what are we going to be talking about? First, what is deep learning? It's this buzzword that gets thrown around a lot. Then we're going to have a linear algebra refresher, followed by 3 models increasing in difficulty that are deep models. The first one is your basic feed-forward neural network. Then we're going to do an unsupervised model, which is a denoising autoencoder. And then I'm going to show how to piece these together to make larger complex models that deal with really complex input spaces. So first, what is deep learning? I don't like to make this analogy too much because it's not that accurate, but you can think of it as loosely based on the brain in as much as it forms a hierarchical representation of your inputs. So the same way that we like to think about abstract objects, we think in the smaller details piecing together to form larger concepts. Deep learning is all about trying to untie or untangle the factors of variation in input by piecing together its smaller components. And what does this do? This ultimately learns a useful representation of your input space that you can then use traditional machine learning algorithms a lot more effectively on. And a useful representation is this thing that tries to explain away complex features by piecing them together. And why is this useful? Well, what you're doing is you're automating feature engineering. And feature engineering right now in traditional machine learning methods is generally the hardest part, figuring out what features, what combinations of inputs you're going to do to ultimately get the best output classification. So how does deep learning actually do this? Well, the short answer, it's a composition of nonlinear transformations, and I'll show you how that's working. But actually what this enables us to do is be a universal function approximator. So it's been shown that a deep neural network, 2 layers deep, with the right parameters, can approximate any input function. And they work just like Legos. So you can stack out the inputs, piece together the smaller components to middle layer representations to higher layer representations, and you can stack them as many times as you want. And this modularity is one of the key components that lets deep learning work with many different types of inputs, as well as have very complex networks that define useful tasks. So there's a little bit of visualization as far as this hierarchical component that you can see. On the left is your traditional, I believe this is from an RBM, but you can see that the lower layers learn lower level features, in this case edge detectors, that can be pieced together to form noses or eyes or mouths. And then ultimately you can have individual face detectors, and this is all done pretty much unsupervised. Same thing for linguistic representation. You go from the syllables to the words, and these utterances get pieced together. Another visualization, instead of faces, this is with objects. You can see lower level layers are still learning the edges, and then you go into more complex feature spaces until you have the higher levels actually recognizing specific objects, like there's a soccer ball pattern and a car pattern. So in order to understand how these nonlinear transformations are working, we have to go a little bit into linear algebra. And that's all this is. All deep learning is a matrix multiplication with your inputs, and then you squash it with some function. So as a refresher, with linear algebra, you have, if you want to draw a line, that's going to be your regression line through some data. You can have your output represented as a matrix multiplication, which is going to be your, in this case, a single dimension is going to be your slope m times your input plus some bias. Now, if you have more than one dimension, instead of just x, you have x1, x2, x3, so on and so forth for all of your inputs. You have separate weight value that you multiply for each of them, and that can be rewritten as a matrix multiplication, which is what this is. So linear algebra is going to have a linear affine transformation of your input, x, multiplied by some weights to produce an output value that you expect to have, plus some bias, but the bias isn't that important in literature. So for a nonlinear function, all you're doing is you're taking this matrix multiplication we just did, and you're going to squash it through some nonlinear function. In this case, we're going to use the sigmoid logistic function, which makes everything between 0 and 1, no matter what the input x was. So we can rewrite this as that nonlinear activation function on top of our matrix multiplication, which turns into this being the actual equation for the logistic sigmoid function. So now that we can force outputs to be between 0 and 1, we can think of them as probabilities, which is very useful later on. So in essence, what the most basic neural network we're going to do today is performing many logistic regression functions in parallel. That's essentially what it does. So you have multiple hidden layers which are layering on those logistic regressions to each other, but in essence, all it does is it takes that input value, it multiplies it by the weights matrix, it squashes it through that sigmoid function to be between 0 and 1, and then it can take that output, feed it as the input with more weights to another layer that does the same exact thing. And you can chain these operations together until you have your final output layer that's still between 0 and 1 because you're still squashing it with a sigmoid function, and that you can represent as your output class probability that you expect. So we're going to actually code one of these using Theano, and you can see how easy it is to just translate the math into code using this framework. And we're going to use the most basic neural network toy problem, which is the MNIST handwritten data set. And what that is it's 60,000 or 70,000 hand-drawn images of 0 through 9. And the input size is 28 by 28 pixels. We're just going to squash it into one large vector. So we're going to ignore any two-dimensional attributes. So a little bit of setting up how we're going to do this. We're defining our input space to be a single image, which in this case is going to be 1 by the 28 times 28. Then we're going to feed it through a single hidden layer before we go to our output. And our hidden layer is just going to be exactly what that logistic regression was showing before. We're going to squash the sigmoid times the weights and add on the bias vector. And the parameters that we're going to be learning, these parameters are what we're going to actually be tweaking as the algorithm goes along to increase its classification accuracy, are the weights and the bias matrix and vector that we're doing. So that hidden layer is the intermediate representation that we're then going to feed in to your last softmax classification layer. So instead of doing just the logistic sigmoid function as the squashing nonlinear, we're actually going to do a softmax, which enforces everything to be a probability so you don't have a sum greater than 1. So in this case, we're going to instantiate a second weights matrix and a second bias vector. So the 4 parameters that we're going to learn are 2 weights matrices and 2 bias vectors, and that's it. And it's going to be able to take this input image and actually classify a 0 through 9 digit representation. Okay, you can see that all right. So whenever you go into a machine learning problem, it's most useful to kind of get a little visualization of what your input data is going to look like. So here I'm just going to do importing some stuff to make it so we can show the images in line, and then I'm going to look at what the shapes of the dimensionality of the input data are. When you take this code from GitHub, you're going to have to download the data set from the URL there and put it in this folder data/mnist. So as you can see, it loads the data into a train, a valid, and a testing set. And this is important, especially in machine learning, because you don't want to overfit by just training and evaluating your model on your trained accuracy as you're going along. You need this notion of having a validation accuracy and test accuracy on data that you're not actually training your model on. So that way you can get a better idea of how it might perform in the wild. So you're not going to overfit just by memorizing your input training set. So in this case, yeah, we have 50,000 examples of 784s, that 28 times 28 image squashed. And then the label is just going to be a single number. So it has 50,000 there, and then 10,000 for the validation and test sets each. And now a single example of an input. This is the input vector X that we're going to have to the entire network. It's 784 numbers. They're all between 0 and 1 because it's grayscale. So that's what the input actually looks like. And that turns out to be the number 5. So that's what our input data looks like. Now we're actually going to have a little helper function here that translates it back into the 2D image representation so we can kind of see what they look like. And here are the first 25 numbers in this data set. So now that we know what our data is, we can actually start writing those equations that transforms it, squashes it, transforms it again, and then puts the softmax. So in Theano, it works exactly as you would be writing equations. It's a symbolic math library, so you need to create symbolic variables, and then you can alter them using math, and then you compile a function at the end that allows you to feed in an input and get out the output of what that symbolic variable would be as the equation. So we're just going to do the basic Theano imports, import Theano and import Theano.tensor, commonly abbreviated to just T. And we're going to create our input variable X. And we're going to make it a matrix because even though conceptually we're going to feed each image in one at a time, to speed things up, we're actually going to do it in parallel. So instead of having a 1 by 784 vector at each input, we're going to have and a batch size of 784 vectors so that it does them in parallel. So we're going to make a matrix that represents that input that we're going to feed into our equation. So now we just write the parameters that we're going to have to multiply and the equation for the hidden layer. So in deep learning, what's kind of important is the initialization scheme that you're going to initialize your parameters with, in this case, the weights and the biases. The biases are most normally just initialized to 0. And the weights, there's a lot of literature on it, and it's a highly active research area. But in essence, you want to follow some of the rules of thumb that exist in a lot of packages today, or you can actually see in the literature. In this case, we're going to do a very simple initialization. We're going to take a uniform random number between the square root of 6 divided by the dimensionalities of our input. And this is from literature as initialization scheme. So we're going to actually create our parameters because they're not going to be symbols in the equation. They're actually going to be something we have to tweak. So we're going to create them first as concrete numbers with NumPy. So what we're just going to do is we're going to take a NumPy random uniform distribution given the size. The matrix we need to multiply our input is going to be 28 times 28. by 500. And the 500 there is going to be the number of hidden units we're getting out as the output. Right? So if you have a 1 by 784 multiplied by a 784 by 500 matrix, you're going to have a 1 by 500 matrix as the output. So when you're doing that dot product. So 500 is going to be our hidden layer output size. So we need to initialize this weights matrix to fill both of those sizes. And we make it as a numpy array. And finally, to bring concrete values into Theano, you have to do something called making it a shared variable. And having a shared variable in Theano just means it has a symbolic wrapper to that number that you gave it, and you're allowed to update that over time. And whenever you reference, it's basically just like creating a variable, but Theano needs it to be its specific format when you're using it with equations. So we're going to create the matrix, the bias vector, just to be zeros, and then we're going to make shared variables out of them. And then finally, we're just going to do that very first step in the equation, which is going to do a nonlinearity. In this case, we're actually not going to do the logistic sigmoid. We're going to do a tanh, a hyperbolic tangent function, which is given in Theano as well. You could easily write sigmoid there. And then we're just going to take the dot product of the input times those weights we made and add it to the bias. So that's just the equation form. So it's x dot wx plus bias, and then we squash it with a tanh. And it's all really quick because we're not compiling the function yet. Now, we repeat this process, exactly what we just did, again, for the hidden layer to the output. So we create the weights matrices again. These are the parameters we're going to be updating. So we create it as a numpy array first, and then we're going to make it a shared variable. In this case, because the hidden layer size we just did above was 500, we're going to go from 500 to an output size of 10. And we have an output size of 10 because we're going to have a probability for each label class, 0 through 9. So the first index is going to be the probability it thinks that the label is 0, and so forth. So that's the only difference there is. The other was, as we were doing before, to actually force it to be probabilities, we're doing a softmax function instead of the tanh like we did in the intermediate layer. But otherwise, this is the symbolic equation form of getting our outputs given our hidden layers. And because our hidden layers are already calculated symbolically, it'll know to use the input x. And then finally, if we want the actual number that it's predicting, we're going to have to do the argmax, which is what is the highest class index of that the output gave. So that would give you, if 0 was 0.5, and 1 was 0.3, and then 2 was 0.2, and then the rest were 0, that'll give you the output 0 because that had the highest probability. And that's what our model thinks the label is given that output. So y hat is going to be our predicted label. It's going to be a concrete number, 0 through 9, just from our probability outputs that are given from this equation. And that is the model. Now to train it, we have to have some notion of how well the model did given what the actual label was. And it's in comparing the actual output through this cost function with the true label that we can try to then make the model more correct over time. So we're going to need to create another symbolic variable to represent the actual labels, because we're going to create an equation that represents the cost or the error that this model is going through. So our correct labels, we're going to make it a vector of integers because that's the format it is. You get 0 through 9 for however many batched examples we're going through. And then we're just going to do the log likelihood. And I should do a slide here first on the cost function. Yes, so the cost function, because our output is squashed to probabilities, we're ultimately getting this vector y. This would be actually 9 numbers rather than the 3 here. But we're getting this output vector y of probabilities that we think the label is. And if we want the negative log likelihood, which is a very common way in machine learning to measure the cost of a function, so what you can think about log likelihood as being is the likelihood that your model was correct given the input. And we take the log of it to make it work better over time because the values can get very small. whoops. I'll present this actually. So in our case, if you take an example output of y being the 0.4, 0.1, 0.5, if you did the argmax, which is what our y-hat is, you're going to get the label 2, because you can see here 0, 1, 2. 2 is the index of the highest probability value here. But when we're taking the cost of it, we want to actually know the probability that we thought was the correct label. So when we're getting the cost function, we're actually going to take here, we're going to take the probability value that we thought the correct value was. So in this case, if the correct value was actually 0, we're going to take the index 0 of our probability output vector, which will give us 0.4. So that's what we thought the correct label probability was, and we were incorrect this time. And then we're just going to take the log and the negative mean of it. And that's very commonly used. That's called the negative mean log likelihood of your cost, which is a way to measure how correct your model was given the actual input label. So here we're just going to do that. We're just going to take the log of the correct label position in our output vector. Y is our output here. And we're just going to take the value that was the correct position value. And then we're just going to take the negative mean of that log likelihood. And then finally, we're ready to start calculating the updates of the parameters to actually make it learn something and classify really well. So we're just going to make a list of all the parameters we gave, which are the 2 weights matrices and the 2 bias vectors. And then we're going to take the gradients. And one of the best parts about Theano, as well as some other packages that can do automated differentiation, is that given an arbitrary equation, it can calculate the derivatives or the gradients of it over time of the cost with respect to some parameters, if it's differentiable, of course. Luckily, most of deep learning is differentiable. So Theano, if you just want the gradients, you can call t.grad, and you give it a cost with respect to the parameters, and that'll give you back a dictionary of the parameter to its gradient. And what a gradient does is it tells you in what direction you should move the parameter number to make it increase or decrease the cost or increase your accuracy. So essentially what it's doing is it's telling you if you should wiggle it up or you should wiggle it down. And then we're going to define how much we want to take that wiggle step later on with something called a learning rate. But the gradient is necessary to help you learn the parameters over time, which direction you should be moving them to make your model lower its cost. So we have our gradients and we have our parameters list. So now with the learning rate, what we're going to do is create these update tuples of that parameter to what the next parameter value should be. And as I was saying before, with the gradient, it just tells you really the direction you need to go. The learning rate is what you're going to do to scale how much you're actually going to concretely change the value. So in this case, we're going to map the parameter, the original parameter, with the parameter minus a learning rate times the gradient, and that step will go in the correct direction to lower our cost. And we're going to do that for each parameter and gradient in the list that we got out here. So these updates map the parameter to what its next value should be. But we haven't actually hooked that up to the model to let it change those values over time. So when I run this, what we're going to do now is compile everything together. And this is what allows the model to learn. You're going to need a function that has the training function, which is going to take your input. It's going to take the correct label so that it can calculate the cost. And it's going to take those updates that we just calculated so that it can correctly move the parameters on its own. And these updates in Theano tell a function to change the mapped value here, in our case parameter, with the output value of that second indexed part of the tuple. And that's how it tells it to change it every time you run that function. And then we're going to have a test function here without that update section, because when we're testing on the test data, we don't want it to learn anything, so we're not going to give it the updates. So it forces it to not change the parameters. One of the downsides of Theano is compile times, especially with very large equations, can take a while, and also depends on your GPU speed. This should compile fairly quickly. Yeah, OK. So that compiled. Of course, it's going to be in fractions of a second if you're on a Titan X GPU. Another thing to mention is that Theano works both on the CPU and your GPU. And in general, you want to use it on the GPU because you're going to get orders of magnitude speed increase. Just because the sheer size of the matrices you're multiplying together, GPUs are very optimized for doing those operations. Now we're ready to actually do our training loop. And what we're going to train with is something called stochastic gradient descent, a fancy way of modifying it with some momentum. But essentially, what you're doing is you're going to iterate, in our case, over batches of the data, because we're doing parallel processing, but you can still think of it as single examples at a time. So you're going to iterate over every part of the data, and you're going to feed it through that training algorithm. It's going to calculate the update that the model should make for that single input data piece to make the cost function lower. It's then going to change its parameters very slightly to make that cost better. And you're going to do this for every data in your data set. And then you're going to loop through that whole process a bunch of times, and those are known as epochs in the literature. So it's an online method that goes through either batches or single bits of data at a time. And at each step, it kind of nudges the model in the better direction to lower your cost. So that's how you learn something over time. And then there are just fancier methods for updating the parameters that lead to better or worse training. We're going to do the most simple, just stochastic gradient descent. So we're going to have batches here, but you can still think of it as single examples. But in this case, we're going to have 100 examples at the same time. We're going to have matrices instead of vectors. Going to check it every 3 times. Let's make that 10. OK. And so to calculate the number of batches we're going to loop through, it's the length of the entire set divided by our batch size. Fairly standard integer division there. And now for the number of epochs, which is every time, an epoch is a loop through the entire data set. So we're going to do that for a set number 300 times. Normally, these algorithms converge pretty quickly if your training algorithm is set up well. So we'll see the cost go down quite dramatically in the beginning and then kind of even out. So for every index of batched data in our training batches, we're just going to extract out that matrix of examples. So in this case, instead of for the index in the range of the train batches, you could think of it as for element in training data set. We're going to take out what that example is. We're going to take out from the correct labels what the labels are. And we're just going to call that Theano function we compiled before. And what we do is we have to give that the input. We give it the labels, because that's what we defined its inputs to be. And then we're going to get out the ultimate cost that we had. And so we can watch the cost go down over time. And then we're also going to get out some prediction values by using the test function, just to get an idea of how's it doing over time. We can start to see its actual predictions. And then we can make an accuracy measure by whether or not the predictions were correct. And we're going to do the same thing for the valid and test sets. It's just the same thing over again, except we're not going to use the flearn function or the ftrain function. We're going to use the ftest function so it doesn't modify it on the valid and test sets. And we're just going to keep looping through that. And then every 10 or so, however much you want to define, every 10 epochs, it's going to save an image of what filters it's learning. So what's cool is that, especially on the first weights matrix that we did, the WX that goes from the input to your hidden layers, if you take the transpose of that, you can put it back into the image space. So you can take a hidden value and transform it back into the input X space. And then we can make an image out of that. So we can kind of see what this filter weight is learning by taking its transpose. And we're going to save that as an image just so we can kind of see a checkpoint over time of, are these filters looking like they're learning, edges? Or are they looking like they're learning curves or numbers, stuff like that? So I'll get this running. Already have an error. That's great. Oh, memory error. Oh, I have too many of these instances running. I'm going to have to shut some of those notebooks down. Yeah, that's the thing with having a lot of things running at the same time. Because the model sizes are very large, and memory is relatively small in RAM. Although luckily, Theano, I think, caches some of the functions. So the second time, whenever you compile a function after you've already compiled it, it's always a lot faster. That's a good thing. And now we can start training. Theoretically, I won't get the memory error. Good. OK, cool. So this is the very first epoch, second epoch. You can see it going in real time there. The cost started out at 0.92. It's already pretty much halved in the beginning. And the accuracy, you can see, started out pretty well. Test accuracy started at 87% by going through the entire data set and updating the weights first. So that's after the first epoch. And it's starting to even out. And we'll save some of those filters. And I'll let that run for a little bit. But essentially, what the model was just doing are these two equations. And that's all we did. And the accuracy is already in 92-ish% given an image to an output class, which is generally pretty hard because the input dimensionality is 784. And that's fairly large given other machine learning problems. Now, one of the issues I said before when you're monitoring your validation and test sets, you want to prevent something called overfitting, which means your model is just going to learn what it's trained to learn, and that could have a bad effect for actual real-world use of it because your training set might not actually represent what your real-world data is. So there's stuff called regularization in machine learning. Commonly, L1 and L2 are used in other regressions. In neural networks, you use something called dropout. And what this does is it randomly masks some of those units. So we had 500 hidden units in our hidden layer. It'll randomly drop out some of those to 0 so that they can't influence the output in that given epoch. So what the dropout's doing is it makes the dependency of certain neurons, it forces that dependency to not, it forces it to not be dependent on some neurons. So some of the connections, it can't be guaranteed that a connection is going to be there. So what that does is it forces a more distributed representation across neurons because you can't focus on some neurons being there all the time. And that increases the ability for the model to adapt to real-world data rather than just strictly memorize your input training set. In essence, it's adding noise into the model. And that kind of leads us to our second model. But first, I want to kind of see the results here. Oh, yeah, we're in the 94% accuracy over test accuracy over 10,000 images, 95% now. We can see some of those filters, MLP filters. See, in the very first instance, it's going to look like random white noise because that's how we initialized it. However, if we go to like epoch 50, you can start to see it forming something. Some of them have curves in them. It's still really early. It's only epoch 50 out of like 300, but it's still getting better by the amount. You can start to see things forming in this white noise. Now, the notion of dropout and adding noise to the model to make it work better on real-world data is what's going to be the basis for our second model, which is going to be the unsupervised model. And unsupervised learning is when you don't have labels of the input and you just have inputs, either a sequence of inputs or they could be out of order. And what you want to do in this case is you're trying to create a representation from just your input data set that you can then sample from and make it a good representation that is useful for other tasks later on. So in this case, we're going to make a model called the Denoising autoencoder, which basically just takes the input, puts it to the hidden space just like we did before, and then retranslates it back into the input space. And we're going to use the error between our retranslation back into the input space and the original input to define how well it's doing over time. And you'll see what's cool about this is that when we're trying to decrease that error rate, after that transformation, what you're doing is you're learning a hidden representation that allows you to reconstruct an arbitrary input from your input data set. And this notion is actually used in things like cleaning missing values in a database. So if you have a large database that has some messy, noisy data, you can train a denoising autoencoder on it and help reconstruct some values that you would expect to be there. And it'll be what's probabilistically most likely. So what we do is the same exact thing we did with the MLP, your normal feed-forward net. The first part is to make the hidden layer from your input layer using the weights matrix and then some nonlinear squashing function. And then what you do for the autoencoding part is instead of going to the output y, which we had before as probabilities, what we're going to do now is put it back into the x space. So when we're doing the transformation back into the x space, we don't have to have another weights matrix because we already have the weights that can transform it from the input to the hiddens. And if you just do the transpose of that weights matrix, you're going to get the hidden space back into the input space. You're essentially undoing the function that you did for your encoding. And this is known as the decoding function. And then we do a different nonlinear function. It can be the same nonlinear function just to squash it so we don't have linear functions piling on top of each other. And that's all it does. That's a normal autoencoder. And what you're going to do is you're going to minimize that error that you had, which is what you expected the x to be and what it actually was. You're just going to do the squared distance error of that. Now, the denoising autoencoder just adds one step to that encoding and decoding section for a normal autoencoder. The denoising one takes the input, adds some noise to it first, and then it reconstructs from the noisy version of your input. So what you're going to do here is we're going to have a separate function that adds noise to an input so that we can then feed that as the new x. And what's kind of cool about this is that you're learning the vector field of the probability of your input given a noisy version of your input. And that, I think that has a pretty powerful connotation for things like filling in missing values of databases or other large unsupervised problems, because you're learning what's the probability distribution of your actual input space. And essentially what you're doing is that you can repeat this process. You can have it start generating data as well. So you're not stuck to classifying like you are with the MLP, where you given an input, you get out the output probabilities. In this case, because we're putting it back in the input space, we can easily use our generated input as the next input in our series and chain them together like that. So in the case of a denoising autoencoder, you just take your original input you want to fix it on, you add noise to it, you translate it into your hidden space, and then back into your input space through the autoencoding function. And then you take what you just gave out, you add some noise to it, and you do this process over and over again. And if you do this to infinity, you're actually going to get something that estimates the original data distribution as a whole. And it'll walk around the field of your input data space, which is pretty cool. So it's, again, pretty easy to code this up once we know those equations. So we're going to have, again, the same exact input size here. It's going to be 1, or batch number, by 28 times 28. It's going to be a matrix. And then we're going to have to create the noise function that'll corrupt it. And what we're going to do is salt and pepper, because our input space is binary, 0 or 1 values, or between 0 and 1 values. Salt and pepper forces some values to 0, forces some values to 1, and it's basically adding the white noise. Then we're going to do the hidden layer computation. In this case, instead of having 500 units like we had with the MLP, we're going to have 1,000. Just because we're adding so much noise every time, you want to have more hidden units than you have your dimensionality of your input, because you don't have to care about it just memorizing. So with the MLP, we had 500 units to make sure it wouldn't memorize and have just neurons map from an input configuration to what the output should be. But here, because there's so much noise, we don't have to worry. So we do the hidden layer the same exact way as we calculated in the MLP, which is just the matrix transformation of our input, now our noisy input, and squashing it. And then the output is just going to undo what we did in the hidden layer. So we're just going to multiply the hidden layer by the transpose of our weights, and then we're just back in the input space. And we're going to have the error be the reconstruction error, which is the distance between our output x and what the original x was. So what's kind of cool here is this is an example output of what this model does. Is given an input here on the left, you read them left to right as, or you can think of it as batches. where batches would be this entire matrix. And we add noise to the input. So this is what our noise salt and pepper function is doing, basically adding white noise. And then the reconstruction is the model gets this noisy input, and it's predicting that this is what the output, or this is predicting what the original input was. And it's pretty close. You see the first number was a 9. It thought it was a 2, but can you really look at that image and see a 9 in it? And it's learning to get rid of that noise very well. So I'll show some code, just see how easy it is again to code up those two equations, basically doing the same thing as here. And what accuracy are we now? 97% accuracy. I think it'll get up to 98 point something eventually, but I'll stop that to not run out of memory. Okay, denoising autoencoder. Cool, so I'm just gonna have all the imports again. We're gonna look at what the shapes are again. Actually, I think I pre-ran this. No, okay. Well, yeah, it's the same exact input that we had before, nothing new there. Here we're going to put all our hyperparameters up here, just because it's better practice when you're actually going to be writing these as models. You wanna make it, as a class that you can add these arguments into. So we're going to have our input size, which is the 28 by 28 matrix. Our hidden size we can have as a variable. When we're initializing our weights matrices, we're going to actually use a Gaussian, or no, it's uniform. I don't know why I have the mean and STD here. Yeah, sometimes you do a Gaussian distribution rather than a uniform one. So you can have that. Or the interval for the uniform one we're going to have be the same as we had before. Then the noise level, because we're writing a noise function, we can have that as a parameter, and so on and so forth. And again, we're just going to make a symbolic matrix X be our input, and we're going to initialize our parameters, all the parameters at once right here, same way that we did it last time, except we only need WX because we're just going to take the transpose of it later. So I'll let that run. Nope, import numpy didn't run the first one, I guess. Okay. So now we have that little pesky thing where we added noise to all the inputs, right? And when we're testing it on the validation and test sets, we're going to assume that the data that we're giving in is going to already be noisy. It's going to, because we're trying to simulate our real world data. So what we want to do is we want to not add the noise into our model on our validation and testing sets. We're just adding it on the training set. So in Theano, there's something cool called a switch that lets you actually change an if statement, basically, inside an equation as it's running. It's a symbolic if statement. So what we need to do is we create a shared variable that's going to be a binary 1 or a 0 that's going to represent this switch, where 0 will be, it'll go through the first data path, 1 will be, it'll go through the second data path. And we're just going to call that a noise switch. And the shared variable is what we've had to do whenever we create a concrete value into a Theano equation graph. And then what we're going to do is we're going to define our salt and pepper noise function here. And it's basically just a masking noise. So we're going to take a random binomial distribution, 0s or 1s, and we're going to multiply by the input, either forcing some of them to be 0, forcing some of them to be 1. And then ultimately what we're going to do is we're going to return the switch statement that lets you basically, given the value of the noise switch, either return the noisy part or just return the original non-noisy part. And we can change that switch variable at runtime, and it'll give us the appropriate output in the equation. I'll run that. Cool. So now we just need to define the model, and we're just going to do it all at once right here. This is all a denoising autoencoder is. Remember, as I was saying before, you can take the input you already had, add noise to it, and then retransform it back in the input space and keep chaining these operations together in that markup chain. That's called something, Bengio calls that a walkback, because given an instance of our data, we can generate many predictions of what we thought it was and have the algorithm kind of walk around that data space, adding noise to it, reconstructing it, adding noise to it, reconstructing it for a certain number of times. And all this does is it speeds up training if you have it walk back around a few times. So what we're going to do is we're just going to chain these operations together in a for loop, and for how many walkbacks we said was probably 5. We're going to first add noise to our original input x, in this case, our inputs is going to be a list because we're going to have to chain them. So we're going to start our inputs list with just the input variable x. We're going to add noise to it with our salt and pepper. Then we're going to transform it to the h space with the dot product and the tan-h squashing. And then we're going to make a reconstruction. In this case, we're going to use a sigmoid because it's going to be between 0 and 1. That's because our input images are all between 0 and 1. And we just take the transpose of our weights matrix here. And then we're going to add that reconstruction on the end of that list so that we can, walk through it again, add noise to what we just thought was the next input, so on and so forth. And then we're just going to take the list of all of our reconstructions at the end, which is going to ignore the original input. So we're just going to take the first index onwards for our reconstructions. So now we have a list of what we thought that input should be given our noise and our transformations. And we're just, to get a concrete actual guess of the one so we can display an image of it, we're just going to take the last one in that walkback series. That doesn't matter so much. You could take the first one. It's generally taking the last one. And we're just going to define the cost again. And in our case, we're going to do the binary cross-entropy cost function, just because that's used a lot for binary input and output spaces. And one of the things about deep learning is you have to kind of know where your data is falling and what your outputs are falling under to get the appropriate cost function, to get the appropriate nonlinear squashing functions, and to make sure the model can actually learn something. Because if you used something like just the squared error here, it'll learn something, but it won't be nearly as effective or as quick as if you used a binary cross-entropy, just by knowing some information about your data. So we're just going to take the sum of all of the average binary cross-entropies between the reconstructions we thought the input was and what the input actually was in our list of reconstructions. And that's going to be our cost. So we do the same thing again when we're going to do stochastic gradient descent. The process hasn't differed at all. We have our list of parameters. We automatically find the gradients. And then we have a learning rate that tells you how much of a step you should take each time when you're wiggling the parameters to make the cost function go down. And then we compile the Theano functions again. In this case, because we don't have the output labels, our input is just going to be the x, because it's an unsupervised problem, but otherwise, this is the exact same as the MLP was. That should take a little bit to, that compiled quickly. Okay, and we're just going to do the same exact stochastic gradient descent. We're going to use that handy helper function for creating an image from our 784 vector again, just so we can see outputs over time. But other than that, it's the exact same. And this one takes a little longer because at every data point, instead of just making one output prediction, you're making 3 or 5, I forget how many walkbacks we have. We have 3 walkbacks. We're making 3 predictions at each step. So it takes a little bit longer. And as you can see, the cost is decreasing. The learning rate's also decreasing. I think I didn't mention that we are doing something where we lower the learning rate over time. And what this does is it prevents, it helps the algorithm find the optimum better, because if you have a large learning rate, you're going to take a large step in the direction each time, and you can actually overstep bounds and actually make the algorithm worse. So this is called annealing. If you lower your learning rate through some decay function over time, you're going to start out in a larger jumps around the parameter space, and you're going to then start settling in with smaller steps over time into what the more likely is going to be the global minimum. So that's just another technique and well documented. So the cost is going down pretty well, and the learning rate is on this, I think it's just an exponential decay. And you can see some of the images. So training and test. Okay, So training, our input image is going to be divided down. It's going to be divided down the middle here. You're just going to see what the input was here, and then what its output reconstruction was. I'm not showing the noisy version that it's actually seeing as the input. So you can see it's struggling a little bit, but even after the first 10 epochs, it's starting to reconstruct them pretty well. And you can see the filters that it's learning as well. The same method we did before. This is just visualizing the transpose of that weights matrix. And it's already starting to show some of the numbers in the middle. And I'll post up some GIFs of actually these going over the epochs, so you can kind of see it evolve over time, what the filters it's learning. And I trained it for 50 epochs before. So here's a test set. So this isn't adding any of the noise in. This is just giving the input, what it thinks a reconstruction of the input was. And it's pretty good. Again, it struggles a little bit with the 4 here, thinks it might be a 9. But hey, data's messy. And the cost will keep going down. Like training this to like 300 to 500 epochs with just your standard stochastic gradient descent makes it perform pretty well. So that's how you write those two models in straight Theano code, and that's you're making the equation version of the equations from the papers, and compiling it all together in functions. As part of my master's research, I wrote a lot of code that had models implemented in it and made them kind of flexible. And I decided to clean that up a lot and actually release it as an open source project, and that's what OpenDeep is. So I'm going to show a few examples of how to make these models in OpenDeep. It's a modular way to be able to connect arbitrary layers and create very complex networks. So in OpenDeep, for our first MLP example where we made just that input to hidden to output, we can add as many hidden layers as we want. And you can think of each layer as a basic building block, and it has some hyperparameters. In our case, we have input sizes, output sizes, initialization schemes, that nonlinear activation we want to do, if we want to add noise or not. You can have all these different configurations. But if we just wanted to make a simple MLP with 2 hidden layers and an output classification layer, all you do is add, first create this prototype, which is a container that you can add layers to make a model. You can think of it as a model, but each layer acts as its own model. You can add a dense layer, which in our case is that basic matrix multiplication from the previous input, and then some nonlinear activation function. So we're just going to do the 28 times 28, which is the 784 input size. We're going to make the output size 1,000. It can be bigger than the 500 because we're going to add that dropout noise for regularization, as we talked about before. We're going to have the hyperbolic tangent activation function for that layer. Then we're going to stack on top of that another layer that takes the input, or it takes the output of the layer before it as the input for this layer. So you don't have to actually specify that connection in this prototype instance. So we just give it the output size. We're making another 1,000 hidden unit layer. We're going to do the other same parameters as the first layer. And at the end, we're just going to put on an output classification layer. Softmax is used for classification with an output size of 10, 1 for each digit. And then instead of having to write all that training code as well, I have a lot of different optimizers. So you can use the stochastic gradient descent optimizer, fancier versions like add a delta, add a grad, that manage the learning rate for you over time, that are generally better. RMS prop, all the popular ones exist. And all you do is you give that optimizer your model, the data set you want, and all the other parameters like the number of epochs you want to go through, the batch size, which is the number of examples in parallel you want to go through, the initial learning rate, if you want to use these fancy momentum parameters. And then also give monitors so you can look at different values of the model over time and actually graph them out as it's going. And then it trains it. So the point of this package is just to make it easy to modularly throw everything together. And it has all your popular models in it that you'd want to find, like Denoising autoencoder is just its own model, so you can, create, well, a fancier version of it called the GSN, but you can just initialize it here and then train it with an optimizer without having to worry about writing all that boilerplate code. So there are a lot of popular packages. So OpenDeep is there. Keras is very popular as well. There's Lasagna. There's PyLearn 2, which is now losing favor to Blocks by the same people. So people who made PyLearn 2 and Blocks are the Lisa Lab, which also made Theano, University of Montreal. There are a lot of packages. If you're not in, well, this is the Python group, so it's all Python, but if you wanted to try other languages, in Lua, there's Torch 7, which is commonly used by Facebook, especially, and there's Caffe, which is mostly convolutional, and that's for vision, and that's produced by Berkeley. So that was kind of an intro to OpenDeep, because I'm going to show you how to do the more complex model, which is our last one, using OpenDeep. So our last model is going to really show how deep learning fits like Legos and works in a modular fashion. So what we're going to do is we're going to combine two different types of networks into one and get a good representation of an unsupervised time series problem. So what we're going to do is we're going to have a problem of predicting what an arbitrary sequence of these MNIST digits are going to look like over time. So given a history of the digits in the sequence, say we're going to repeat 0 through 9, 0 through 9, 0 through 9, say that'll be our arbitrary sequence. Given a history, we're going to predict what the next image is going to be. And you can think of this as a video frame prediction problem, where given the previous frames in a video, what do you think the next image is going to look like? So this is an unsupervised problem because we have the sequence and we just care about predicting what the input looks like. And there's a type of network that's gained a lot of popularity, especially because of easy-to-read blog posts like Andrei Karpathy has a character RNN blog post that's really great showing how it works. But the RNN, or recurrent neural network, is very good for having an internal memory state and explaining away time series problems. So it has a connection between hidden layers over time that lets you map complexity over time. The generative stochastic network, which is our fancier version of the denoising autoencoder we just made, is really good at working with complex unsupervised input space problems. And what we're going to do is we're actually going to combine these two models so that they work well together. So we're going to use the GSN to model the input to a hidden space. Just like the denoising autoencoder was able to create a hidden representation that was useful for reconstructing what the input was, that hidden representation is now takes away that input to hidden complexity. Then we're going to do a recurrent neural network between those hidden layers. So we're going to add another network on top of that hidden layer space. So the RNN can focus just on modeling the time complexity or what the sequence looks like. So in that case, we're going to take an input x. We're going to make a hidden value of it, a hidden representation using the GSN. Then we're going to take that hidden representation that has the current time period. We're going to map that through a recurrent network to let it know what it thinks the next time period's hidden representation is going to be. We're going to take the GSN and map that hidden representation back to the input space. And that turns out to be pretty good for this simple MNIST task of modeling this complex time series dependency. So the RNN, how does an RNN work? It works by mapping an extra connection between the hidden layers, as I said before. So you start with your inputs. You can map it at each time step, your input to your hidden values. And then your hidden values also have a mapping to the previous hidden values. You just have to keep what the previous value was over time. And this hidden value gets updated to act as a memory for your sequence. And there are fancier versions. Most commonly in industry, you'd see something like an LSTM, long short-term memory, or a GRU, a gated recurrent unit. And they're basically just fancier versions of this base recurrent network, and they have the ability to capture longer-term dependencies by modifying the way the memory updates in between steps. But in essence, it all works like this. You have some information that's getting transferred between time steps in your model. And you can think of it as a very deep neural network. Because if you unroll it over time, the hidden-to-hidden layer connections, if your sequence is long, say 50, or 50 isn't even that long of a sequence, but if you have 50 time steps you want to model over time, you're unrolling your network into a 50-layer neural network because of that connection space. So you can see it can be pretty hard to train these, but luckily there's been a lot of recent progress on optimization techniques to make that manageable. The GSN, this is just a fancier denoising autoencoder by having multiple layers. In essence, it produces a better hidden representation than the denoising autoencoder did. As I said before, this is kind of the structure of the problem. In our case, U is going to be the recurrent hidden state that gets mapped over time. X is going to be our input. So we're actually, instead of doing the mapping of X to the hiddens first and then to a recurrent back to the hiddens, we're just going to do X to the recurrent layer, and then the recurrent layer is going to actually output what the next hidden values should be, so that the hidden values can then reconstruct better. The RNN is pretty good at mapping the original input to the recurrent memory hidden space, but for predicting and reconstructing later on, we want it to map the output to an easier space. And here's actually an example, just like the denoising autoencoder, of something where it's learning a sequence. As you can see here, you read it from top left to bottom right. We're just repeating 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And you can see this has 2 bits of complexity, right? So each time step, you have to know if you are ascending or descending, and what the next number in the ascension or descension would be in that sequence, right? So if you're on 0, you have to know that, oh, the last one was also a 0, so I'm going to be going up now. And you have to know that the next up is going to be a 1, and so forth. So it has 2 bits of complexity. And I aligned them here, but this is actually should be 1 offset. So you can see with the value here that it's predicting, the 0, 1, 2, 3, 5, 6, 7, 8, 9, that is given the previous ones in the sequence before that output number. Oops. So it's learning to reconstruct what the next one should look like pretty well. And you can kind of see they actually look like the average of all the numbers. And that's to be expected because I'm randomizing it when I run through the epochs, so the sequence doesn't stay exactly the same. It's actually any one of the zeros and any one of the ones, so you're going to get an averaging effect. But it learns to map that pretty well. And in OpenD, we're going to show how to make a model really quickly combining those 2 types of layers, the GSN and the RNN. So we're going to do a little imports. Going to use the max GPU. Then we're basically going to just specify 1 RNN layer, because there's a recurrent layer set up here, 1 GSN layer, and we're just going to have to define how to actually connect them together using some Theano. So one of the issues with an RNN is that the input and output space is 3-dimensional rather than 2-dimensional because you have this extra time sequence dimension, if you will. So what we're going to have to do here is use something called a scan, which is a way Theano loops over things. So it'll just loop over the first dimension in the sequence and do that operation over every element in the time series. So that's just a way of applying a single function across an entire dimension of an input space. So what we're doing here is at each time step, we can think of it like that, we're going to create a new GSN that has all the same parameters and arguments as the original one that we created, but that's just going to map that given predicted hidden value back into the input space. So we just want to get the output for each value each time of what the prediction is, and then we just take that function and loop for everything the RNN is putting in the output, because that's going to be a sequence. Then you have your outputs, your updates, your cost, and your parameters. And in OpenDeep, if you were going to define your own model, you just have to have these methods in here that get your inputs, get your parameters, get your training cost, gets your updates and your outputs, so that the optimizer can actually work and make it learn something. So other than that, should see a lot of debugging output, theoretically. Or not. Oh yeah, because it's not done yet. Here's when you actually instantiate that model. We just define the class for that model. We're going to instantiate it here and the optimizer and train it. And now you can see all the debugging output that I give, this showing, initializing bias variable with 784 and things that you might care about if you want to configure a logger. Now this model, because it's so big, the RNN is going to actually have 100 units, 784 input size. Our sequence length is going to be 50. It has a lot of parameters. This is actually probably going to take too long to compile, or it'll give me an error. That'll work too. Live demos. Oh, I'm not connecting to the internet, so I just have to specify the MNIST dataset where it's actually located, because it's not in the normal place. I also have representations for all the popular data sets, MNIST, CIFAR10, some MIDI data sets, and also ways to wrap your own in-memory objects. You can wrap any NumPy array you might have, SciPy array. I'm going to have it work with H5Py. I want to have a database connection as well, because I know working with data, at least when I implement models for some clients, working with the data is normally what takes the longest amount of time. Okay, GSN compiled. That GSN compiled. Yeah, I just think it'll take too long. But we can see some of the outputs that I had it run before, I believe. Maybe they're not here. Yeah. Well, that's what the output looks like. But you can see it's very easy when you just think of deep learning as matrix multiplications with some input value, given some nonlinear activation. You can just chain these together in very complex ways. And that's one of the big powers of deep learning. So deep learning is a model that learns a hierarchical representation of your input space. And all it's doing is doing a matrix multiplication, some nonlinear squashing function. And it actually learns useful features, and you don't have to anymore go through your feature space and hard code, oh, I want this feature to be like 2x squared plus x 3 or one of the sub-features. But it does need a lot of data. So this is a medium to large data algorithm. It doesn't really work on small data. You're just going to memorize your training set, and it won't translate well. Our first model was the MLP. It's the most simple, normal feed-forward model. You have an input, a hidden representation, and an output. All it's doing is generalizing that logistic regression and uses that dense or fully connected layer. And then we're just having a softmax at the end, so we have probability. A denoising autoencoder is an unsupervised one, where we're just reconstructing an original input after transforming it to this hidden space. And similarly, it's using the same dense layer, or fully connected. That's the basic building block for an MLP. The RNN GSN is combining two of these different types of networks. And because you can compose any input to any other outputs for a model, it works modularly. And it works the same training. So you create this giant equation that represents what your model is, and what you're getting with Theano is automatic differentiation. So you just take the gradients from the entire model at once, and you're able to train it. And that works with backpropagation, if you were wondering how that's actually working. And the same principle can be applied to other large complex networks. The RNN-CNN is a notable one. Relatively recently, Andre Karpathy and some guys at Google came up with it independently that lets you generate text descriptions from an input image. So it uses a CNN, which is a convolutional neural network. It maps that input image to a representation space that then the RNN feeds off of and generates text of what a description of is in an image. And it all worked with the same exact principles. You're taking the gradients over time, you're just chaining outputs of one network as the input for the next network, and then you're defining some cost function. So deep learning, again, is hierarchical, has some basic building blocks. It's just matrix multiplications, nonlinear activations, and when you're training, you're just getting the gradients, which is the direction you should wheel your weights to make it learn something. And it's the same with any machine learning algorithm. You have supervised and unsupervised things, and you can make very complex networks. And that's it. I hope you're able to learn something, maybe demystify neural networks a little bit, maybe helps you want to try out different packages like OpenDeep or Keras or Lasagna or any of these other things. But Does anyone have any questions? Yeah.
So how do you know? You mentioned that it's important to have a lot of data.
Mm-hmm.
It's true for all the machine learning, but is there a specific, more hard requirements for deep learning? Is there like a good rule that you can follow in order to determine, you don't have enough data, you don't even want to start?
Mm-hmm. Oh, yes. So he's wondering, so deep learning needs a lot of data. Is there a hard rule to follow as far as how much data you need for a given model? And how do you know you can apply deep learning given your data set size, basically? So I don't know of any hard cutoffs. In general, you want it to at least be on the same order of magnitude as the number of parameters you're learning. If it's less than that, you're not going to be able to learn the parameters well. In general, in practice, I'd say for models that are like 0 to 10 layers, well, 1 to 10 layers, like the basic ones that we've been programming, you wouldn't want anything less than 10,000 examples, especially if your input space is, on the order of 100 to 1,000 features. Obviously, like with text, it's easy to get large examples. So in that case, we're operating in the order of like 6 million examples. So that is manageable, but I'd say anything less than 10,000, you really want to bother with a neural network for, especially if it's a complex input feature size. If you have like 1 or 2 input features, you're probably better off doing an SVM or normal regression anyways. Yeah. Yeah.
Could you show the last image you had from the first model?
Oh, the MOP. Yeah. 150. Oh yeah, I think we only have the filters here. So this is after epoch 150, the filters that it's learning. Still looks a lot like white noise, but you can see kind of the swirls, parts of a 5, I see in one of them, parts of a 7. And the white noise is actually concentrated in areas where the noise is normally, which is an interesting note, that it's kind of also learning the positioning of the edge detectors and stuff like that. Because inherently this is treating everything, it's disregarding this two-dimensional aspect of it. It's treating everything as an input vector of 784, which is why it's positional in these filters as well. If you have something like a convolutional neural network, which actually is pretty much position agnostic, you'll see things more like in the beginning of the presentation, where it's more angular and things kind of look like they're in the middle of the feature space or in the middle of the map. But yeah. Cool. Yeah.
So that's a general rule of thumb. How much effort would you say one should put into deciding architecture of the neural network? Would you really want to be dealing with things such as gradient optimization or gradient hyperoptimization?
Yeah, so I'm always a fan of start with the simplest model and build it up if it's not working. In most cases, I recommend people to try just like logistic regression first and all your other naive methods, of course. And then to start with the smaller versions of the model. You have to know the right architecture, right? So if you need a recurrent network or a convolutional network or just a simple MLP, you know what those problems are good for. So the recurrent ones over time, convolutional is good for images, and so forth. And you start with like a one-layer version of those. Unless you know that there's literature about the particular problem domain you're in, then you'd want to try one of the model architectures that is kind of drawn out in those papers. So yeah, that's the art of it, right? For the hyperparameter optimization, yeah, that a lot of times is a search process that people go through. Grad student search, where you have your grad students go and try out the different parameters. What's really more optimal is using the Bayesian hyperparameter optimization. And there are some packages out there that can do that, as well as companies, I think, formed around providing this as a service. And that's probably a smarter way to go in practice than to do a random search which is, yeah, so you do a random search instead of a grid search, but you'd rather do the hyperparameter optimization as far as finding the correct parameters. In most cases, though, I'd say that a lot of input types, like text, is really well understood in literature. Anything that's really well understood in literature, you can just take the initializations that they've already done the search process for. And that's what I always end up doing in most of the models that I go through, because I do a lot of text-based things, some image-based things. And so kind of borrowing from papers is the current way that most people do it. Oh, yeah. So I don't have examples as a video, but right, you can imagine each of these being a frame. So essentially, that's what this is doing. There was a paper where a similar model was applied to a red bouncing ball just moving across a frame, and it was able to predict what the image of the next ball should be in that video. But you can think of this as, I mean, it wouldn't look like a nice video to us in our eyes, just because it's going to be flashing numbers for us. But in essence, what it's doing here is predicting the next frame of a video, or the next image in a series, given the previous images. Yeah. I think they're based on the same basic assumption, is that a hierarchical representation of an input is the best way to represent it, just because you have an exponential increase in representational power given a certain size. Other than that, I don't think there are too many people borrowing, at least in the deep learning space, people aren't borrowing ideas from the HTM. I think the HTM might be incorporating some ideas from the deep learning space based on how things are going. I haven't kept too up to date with what they're doing with the HTMs. I've read all on intelligence back in the day. But they're both under the same basic assumption that the brain is operating in a way that lets you form hierarchical representations of some input space. The mechanics, I know, are very different as far as what the on intelligence, I think, outlined as an HTM. The way that works is different from just the matrix multiplication and the transform. Mm-hmm. Mm-hmm, mm-hmm. Yeah. Yeah, definitely memory is a very big research focus, and I don't think that RNNs have borrowed ideas from the HTM, but it's very active as far as how to actually represent a stored memory that you can then do useful things with, right? Because you want an agent eventually that does useful things rather than just classify as still images, or So that's one of the reasons also that RNNs have started taking over a lot, because people have started realizing how good you can represent many problems as sequences. So there are RNNs that can actually generate handwriting that looks like a person's cursive handwriting by treating an image, a two-dimensional image, as a sequence of pixels. And doing a memory of, at what position is the pen down, at what position is the pen up, and at what sequence through in this image space is going through. So it's not just, your normal like text over time or speech over time problems. It can be applied to images. RNNs have also been applied to, well, it's similar to the handwriting thing, but attention mechanisms, kind of like trying to model how the eye is tracking attention over time is a way to think about it. So at what points of your input are you going to look at, and what's the next point you want to look at based on where you've previously seen? So RNNs are very actively researched right now, and they're used for things like that. And I don't know enough about HTMs to know if there's that much overlap. Mm-hmm. Yeah, so it can be either repeated a lot, or like essentially what you want is you want a bunch of different noisy representations of what the sequence you want to learn is. And so you can imagine a video database of a bunch of short videos of hockey being filmed, right? So you're going to have a bunch of the same action happening, but it's going to be a lot of different representations, not the same thing actually looped over. And I think Facebook recently published code that they're using to classify actions in videos, and they're using the RNN-CNN method instead of the GSN. But essentially what you're doing is you're able to learn based on the variety of inputs, still given some output label, this temporal aspect of the video of what should be happening. So I think for actually generating what the next frame is, it's very difficult unless you actually have very close representations repeating a lot. But for things like classification of actions, like what Facebook's doing with their video platform, you can just use a lot of examples and have it as a final output classification. Mm-hmm. Yeah. I don't know if SoundHound does. I think Shazam does. And I know Spotify, I think Spotify's for recommendations. I don't think they do the recognition. But yeah, so essentially what you can do, what those often do is something that is take a sequence and create a recursive kind of fingerprint of what that input is. And that gives you just a single hidden value for that entire sequence. And then you can match that up against a database, see its similarity to other things. But yeah, using the hidden representation turns out to be very useful in aspects like that, because you can take a very noisy input environment. Like you imagine it's people speaking, and have it learn something like that. Mm-hmm. Yeah, so the Andre Karpathy's RNN blog, some people have taken the code that he published on GitHub and applied it to music. I think like folk songs and stuff like that, where it has generated, kind of music. And this model that I have, the RNN GSN, is actually based on a paper from 2012 that works with MIDI. So it's not the actual audio waveform files, but it's the MIDI files. And it's still a bit too complex, mostly because the way music, I guess you could put this in the cost function, but right, if you're slightly off in some areas, it sounds a lot worse than if you're slightly off in other areas, right? So if you go to like a tritone versus like a fifth, that's going to have a small distance in your MIDI space, but it's going to have a huge impact on the hearing space. So I've actually used this RNN GSN to produce some MIDI songs, and they sound terrible. Yeah. Yeah.
What do you think differentiates deep learning from sort of conventional machine learning?
Yeah, so in my mind, it's entirely the hierarchical aspect. So you can kind of layer things a little bit with PCA, does this a little bit, but pretty much methods are just linear. You're going to have some sort of linear or kernel transformation from your input to your output space. In this case, what we're doing is we're stop-gating that linear transformation with some nonlinear squashing or activation function. And what that's doing is it allows you to exponentially increase your representational power. Because if you would just stack linear representations without doing that nonlinear bit, what you're going to do is create a function or an equation that can be reduced back down into a single linear function. You're not gaining any power. And pretty much all conventional machine learning things that are used like SVM or regression is just a linear function. So you're not going to get any representational power benefit if you start chaining your regressions together. Yeah. I don't know. I heard musings on the Theano development listserv that people were trying it. I know people have tried it on like multi-GPU settings, but that's in a single computer with multi-GPUs. So I don't know of any of these being applied over Spark. Yeah, no. But there is a nice way to actually train them distributed. So well, you could parallelize your model and parallelize the data. What's commonly used is parallelizing data. And what you can do is you can set up clusters where you copy your model across the different clusters and have it train on subsets of your data. So you partition your input data over to the different clusters, and then you have your models trained separately, but they're the same input config parameters. And then when they're done with their little batch, they transmit the parameters they learned back to a central server that's going to average those parameters and then send it back out. So you're going to process over your data in a distributed manner, and then use this averaging trick to make sure that your models aren't being very, very diverse. And kind of as the average of the parameters goes along, you're going to learn something useful, most likely. But yeah, that's what's most commonly used for speeding these things up at like very large scale with very large data. Oh yeah, yeah. You have to use a GPU, unless you have massive CPU farms and massive amounts of RAM lying around. Yeah. I haven't actually coded any of those parallel systems, so I'm not sure what their respective runtimes or bottlenecks are. Although in deep learning algorithms in general, most commonly the bottleneck is data transfer. So if you're chunking or streaming from something that has the latency is generally what's going to take up a lot of the time, because you're looping over it many, many times. And you're going to reload it in many, many times unless you are smart about the way that you load things. Although as complexity of your networks increase, the actual model computation becomes the bottleneck. So in lower complex networks, it's the data that's the bottleneck. In higher complex networks, it's just the sheer size of the matrix multiplications you're doing. It's going to be the model that's going to be the bottleneck. Well, so you'd ideally want to fit all of the data that you want to partition for that node into this RAM and have it stay there as you're looping through it, and then refresh the whole memory with a new batch. So you can do mini batches from that set that you load into RAM, but you'd want to fill it up. Again, I haven't used it at scale. I'm not sure. So the models can get on the gigabyte size, yeah. So even the model fitting itself in memory, which it has to do with Theano, I think the RNN-GSN's in the megabytes scale, like tens of megabytes for its parameters, saving them. And it can easily, especially have large recurrent sequence sizes, if you have like 1,000 sequence RNN that you want to be able to compute, you're holding a 1,000 layer network in memory. It's going to be gigabytes.
So if you train this model to output the next digit of pi, how far will it go?
That's interesting. If you train the RNN-GSN to output the next digit of pi, how far could it go? I guess it wouldn't learn anything. I mean, yeah. Actually, no, it would learn. What it'll learn is, oh no, because it doesn't really repeat. Yeah. Yeah. Well, if you make your subsequence size small enough, it'll learn the repeating units in there. Just because that's what it's doing when it's doing the gradients. It's doing it over the subsequence that you're giving it as a specification in the input size. So if you have a subsequence of 100 over time, it's going to learn, when it starts to see those patterns of 100 things start repeating. So it'll learn all of the sub-repeating patterns in pi, which, yeah. Well, some people have tried to, it's not that good against stocks just because of the input features aren't that predictive. But, people try.
Determines the number of layers also. It's kind of like a mystery to me. It seems
Yeah.
everybody has their own thing that they try.
Yeah. So generally, rule of thumb is start with smaller and then just keep building up the layers. One of the rules of thumb in that regards is you'd want to have a deeper but narrower network. And what that means is you'd want to specify your number of hidden units to be less and your layers more before you start increasing the number of hidden units. So in our MLP, we had 500 hidden units for each of those hidden layers. If that wasn't working out so well, I would prefer to add hidden layer before I start increasing the hidden size, because those are the two variables that ultimately determine what your network can learn. The representational power is the number of hidden units and the number of layers that you have. Your overall parameter size, basically, is what it is. So in general, a rule of thumb is you'd want deeper networks and you'd want wider, but start with the first layer. And if it's not working, add another layer, see if it helps. If it doesn't help, play with one of the other things.
And non-working, you mean higher and maybe what would be the indication that it's not working?
Yeah, it's generally just the accuracy on your test set that you care about. The ultimate thing that you're trying to predict, like you're trying to have this model be useful for something, and you have a general baseline idea of where you want your accuracy to be, if it's good enough, or if you need to improve it.
On the upper end of things, it's overtraining on the data where it just memorizes what the training set.
Yeah.
Right? So you can build it up until you overtrain it and then
Yeah, exactly. So a lot of the times, yeah, you build it up until it starts overfitting, then you can start adding noise, or you can start reducing some of the parameters. You just have to know about what each possible like hyperparameter configuration, how does that impact what the model's doing as a representation. So yeah, play around with things like dropout, if it starts overfitting, stuff like that. Yep. All right, thanks everyone for coming out, and hope you learned something.